So I realized that I hardly said anything yesterday in 2 hours. Very impressive. That's what tenure is for, you know. So, but actually, I realized that it presents me with a good opportunity. So yesterday, I was planning on, after saying my very little, to say something. And I was going to first, as I mentioned, first talk about the motivation that led up to the amplituhedron, say a few things about it, and talk about some open problems. And that was to sort of piggyback off the beautiful lectures that we had yesterday on related topics. And then for my second lecture, today's lecture, I was going to tell you about the trace phi cube theory and isosahedra and so on. Now, in fact, sort of logically, the story of trace phi cubed and isosahedra and the connection to curves on surfaces is simpler, is quite a bit simpler, is somewhat more mathematically standard, and much better understood by now than what I definitely feel is a much deeper and more interesting story related to amplituhedra. Okay? But then for that reason, and especially since we just had Caroline this morning, I'm just going to reverse the order of the presentation, which now makes a lot more logical sense. To start with the simpler story, where things can be understood in a much more straightforward way. And then tomorrow I'll tell you something about the open problems related to the amplituhedra. And then if we get there, I'll tell you something about the large N story that I advertised as well. So that's what we're going to do. I'm really going to begin. So before getting into a really systematic exposition of the story, what we're going to try to do today is understand this trace phi cube theory that's been introduced. I'll introduce again. And ultimately, we'll understand it not just at tree level, but to all orders in perturbation theory, because there's going to be some way of thinking about it. Has nothing to do with planarity, non-planar, everything. But the color is important, but other than that, to all orders in perturbation theory. And at least sketch for you how it's related to very simple pictures of curves on surfaces and some very interesting combinatorics associated with these curves on surfaces. This is going to connect to field theory, trace phi cubed amplitudes. You can think of it as a bottom-up discovery of string theory, trace phi cubed amplitudes, at least in some limits. In fact, we went into a larger collection of objects than standard string theory. Standard string theory will be contained in as sort of one corner, one special sort of choice of what this object looks like, but you're allowed to work with a larger world of ideas. But as we'll see, you can sort of get to string theory without 6 months of or a year of a graduate course in the subject. Okay, so that's what we're going to do. But what I want to begin before we get into lots of definitions, and I actually want to begin with the example that Caroline had talked about quite a lot of this pentagon. Okay, so here we're talking about the n equals 5-point amplitude, and as Caroline explained, it's associated with this picture of this particular realization of the isosahedron. I'll also draw, in this case, the mesh that she drew for us. Okay, so the amplitude is a function of these x variables, as she explained. So this would be x24, x25, and x35. And then we also have these meshes, C13, C14, and C24, with the formula that she gave that I'll write down again in a second. Okay, so we have in x13, x14 space, we have this picture of the isosahedron, where that here is C13, this here is C13 plus C14, and this up here is C14 plus C24. Okay? Okay? And so what we're going to see in the rest of the lecture, for this example and many more besides, is where this all comes from. Okay, so Carolina motivated it, but at some points there was a few little, somewhat out of the blue steps, like who told you to draw this mesh? who told you to write the equation x plus x minus x equals constant. All of those things sort of seem fairly simple and natural, but they're a little bit pulled out of apparently nowhere. So I'm going to talk about an alternate point of view for where these things come from, which is 100% rational. Okay, it's 100% rational, but we'll have a couple of magical features in it nonetheless. Okay, so but the moves that you start making are 100% rational. But to give you an idea of what it will be about, I just want to illustrate some of the things that we'll talk about already in this example. Okay, so essentially what we're going to be talking about is a dual of this picture. Everything that I will say later also has an avatar directly in the language of the original polytopes, but we're sort of going to focus on a dual of this picture. And if I start here, we're going to look at we're going to start by looking at the inward pointing normals to the facets of this pentagon. Okay, so that's of course a very standard way to see a dual object. You have a polytope, the dual polytope, the vertices of the dual polytope, or the facets of the original polytope, and so on. So it's very reasonable to look at those inward pointing normals. And if you remember, this was the face where x13 goes to 0. This is where x24 goes to 0. This is where x13 goes to x14 goes to 0. This is where x24 goes to 0. x25 goes to 0. x35 goes to 0. And x14 goes to 0, as you also see from the, x13 goes to 0, as you see from the picture. Okay. So again, this corner is where both x14 and x13 goes to 0. So you can think of this line as associated with this partial triangulation of the underlying pentagon. Just repeating things Carolina said, right? This is associated with this partial triangulation. And so this vertex is where the two of them come together. They don't cross each other, that's good. So they come together there, and we get this sort of 1, 3, 1, 4 complete triangulation. And the same thing happens as we go around. Okay? So all of the things that meet correspond to chords that don't cross, and the vertices where they meet are the complete triangulation that goes along with that, right? So we're first going to just draw those arrows, and if I draw those arrows, I get the following picture. I'm just drawing the anormals, okay? Now, I've chosen to draw the normals so they're all like 0, 1 vectors, right? So they have zeros or ones. We'll come to that point later. I mean, when you just draw normals, there's no meaning to the magnitude of the anormal. But these it's a very reasonable thing to do, and it'll have an explanation later. Okay? But here, this would be associated. I won't keep writing x. That will be associated with 1, 3, right? That's this inward pointing normal. That's 1, 3. This is 1, 4, 2, 4, 2, 5. And 3, 5. Okay? And so what we have here is a picture where now the kind of plane is divided into these cones. Right? The plane is divided into these cones. And this is the normal fan of the corresponding polytope. The dual, these cones are just associated with the vertices of the polytope in the obvious way. Okay, so again, this cone 1, 3, 1, 4 is associated with this vertex, right? It's the two facets that meet at that vertex that's associated with this cone. So again, the point is that this 1, 3, 1, 4, this region is now associated with a vertex, and that's this vertex, right? That corresponds to this triangulation. And the cool thing in this picture is that the plane has been divided into sort of 5 regions, and each region is uniquely associated with a diagram, right? So that's just the dual statement that we had an object whose vertices were capturing all of the diagrams. Okay, so far I'm just re-saying some of the things that Carolina told you in the language of this dual fan. Okay, so this is sometimes called the normal fan of the polytope. Okay, so again, the most basic things are that the cones we have cones, they cover the whole space, and that each cone can be associated with one of the diagrams. Okay. Now, something else that Carolina told you is that this associahedron is naturally presented as a Minkowski sum. Okay? That's a remarkable fact. Just to sort of pause and back up for a second, there's just the zeroth order fact that the combinatorics of diagrams, of triangulations of a polygon are captured by the faces of an object. Okay, that's Stashev's realization. Amazing. That's already remarkable, right? If you like, that's all about Feynman diagrams, related to Feynman diagrams, factorization, you know, all of those words are related to this fact. The fact that the associahedron has a particular realization, not a random one. You know, you can draw it in lots of ways. I could draw this pentagon with sort of sides, you know, tilted with random angles, and then what I'm saying would not be true. Okay, but the fact that there's a particular realization of the associahedron with parallel sides. You see, these parallel sides mean a lot in this picture. Okay, tells us that it can also be represented as a sum of simple pieces. The fact that it's representable as a sum of simple pieces is remarkable, is an extra fact on top of the Stashev fact that the combinatorics is captured by a polytope. And as Carolina explained in her talk, this extra fact has extra implications for the amplitude that we didn't know about before. And this extra fact makes it easy to predict where the amplitude vanishes, and how when you go close to the places it vanishes, it also factorizes. In a way that's not at all obvious if you know something about Feynman diagrams. So this is an extra interesting fact that the associahedron is naturally Minkowski sum. How is that fact reflected in this picture? So let's remember what the summands look like. You know, we had a summand that looked like this, we had a summand that looked like this, and we had a summand that looked like this. Okay, and those of you who know about Newton polytopes and tropicalization and so on are going to know exactly what I'm about to do now. Okay, but those of you who don't, there is something we can obviously do with this picture as well. I can look at the normals to each one of these pieces, right? So the normal to this piece looks like this in the same way, and the normal to these pieces will look like this. You know, look, I guess like this if I'm doing inward pointing. Okay? So notice that if I just draw these guys, well, if I draw this one, it looks like this. Okay? If I draw this one, it just looks like this. And if I draw the other one, it looks like this. Okay? So the fact that you can build the associahedron as a Minkowski sum in the language of the normal of this normal fan is reflected in the following cool thing. This has 5 pieces. So I've made kind of a complicated space, right? That's divided into 5 pieces. But I can make those 5 pieces by laying on top of each other these 3 pictures. Okay? I have this picture, and then I put this picture on top of it, and I put this picture on top of it, and putting all the pictures on top of each other gives us this division of the space into the 5 regions, each one of which corresponds to one of these vertices, triangulations, Feynman diagrams, all the different ways we could talk about it, right? So that's a sort of a well-known statement that the Minkowski sum at the level of the polytope is reflected as a common refinement of the summands at the level of the fan. Okay, if I look at each sort of element, and I look at the normal vectors for each element, I can build the complicated fan by just putting them, stacking them on top of each other. Okay. Okay, so that's how this fact is represented, and now we're going to try to understand this fact better. Now, another 2 things to say in this example. You know, if you're given these summands, and let me call this direction, I'm just going to give these directions names, sort of 1, 3, and 1, 4, okay, as we see in this picture just associated with the normal quadrant here. It's, of course, natural to associate polynomials with each one of these pictures. Okay? So I'm going to associate with this picture, I'm going to associate the polynomial 1 plus y14. Okay, with this picture, I'm going to associate the polynomial 1 plus y13. And with this picture, I'm going to associate 1 plus y14 plus y14, y13. Okay? these are polynomials, which are a sum of monomials, and every monomial just records the corresponding vertex of the picture. Okay? So this vertex is 0, 0, this is 0, 1, and this is 1, 1. And so this polynomial is 1 for 0, 0, y14 for 0, 1, and y14 or y13 for 1, 1. Okay? So those of you who know about Newton polytopes will then say that the Newton polytope of this polynomial is back to this simplex. Okay? The Newton polytope of this guy is back to this, of this is back to this one. The Newton polytope of this guy is back to this one. All right? Okay? Something that we can do with these polynomials, of course, none of this is a coincidence, but I just want to illustrate in this example before we say everything in general. And that's the revolution from this morning. Okay, so erase this. This is drying. Something that we can do with these polynomials is we can imagine what would happen if, I mean, they're all sort of plus signs here, so it's very natural to imagine that the y's are positive. So let's imagine that y13 and y14 are positive. Remember, I promised you positivity is everywhere in this story, and here it is at the very most basic place. Well, for example, we could do this by writing y13 as e to the negative t13. This is a pure convention, the minus sign here. But this convention we like to use is e to the minus t14. So now t13 and t14 just vary over the entire real line. Okay, so and so a kind of a natural question when you look at these polynomials is to ask in t13, t14 space, as you go off to infinity in all possible ways, what do these polynomials look like? As you go off to infinity in different ways, different terms in these polynomials are going to dominate. And so they will simplify. Of course, this is the entire, this is the beginning of thinking about tropical geometry and tropicalization. But I just want to do it in this example. Okay, so remember the logic is we got these summands. It's natural to associate these polynomials with the summands. And now we're going to just ask what these things are not linear. But we're going to ask what they look like as we asymptotically go off to infinity in the positive domain where the y's are positive. And so, for example, what does 1 plus e to the minus t14 look like as the t's go to infinity? This is going to look like e to the max of 0 and minus t14, right? That just says either that dominates or that dominates. And so whoever dominates, we're going to get that guy, right? Let's do the more complicated one. If we look at 1 minus e to the minus t14 plus e to the minus t14 e to the minus t13, this is going to go to e to the max. Well, either 1 dominates, or if t14 is minus t14 is the biggest, that will dominate. Or if minus t14 minus t13 is positive, that will dominate. Okay, so there's really nothing to do here other than just put maxes everywhere. All right? Okay. But now, if we look at this picture, let's do that simple one first. This 1 plus y14. If we just ask, where does so 1 plus y14 is going to e to the max of 0 and minus t14. And so this in t13, t14 space is not a linear function, but it's close. It's piecewise linear. Sometimes it's going to be 0. Sometimes it's going to be negative t14. Okay? And so this has a domain of linearity in positive t14 space, up here in positive, sorry, I'll draw it like this. In positive t14 space, this is 0, and in negative t14 space, it's minus t14. Okay? So this thing is linear down here, is negative T14, is linear up here. And what separates them is exactly the fan that we associated with this little factor. Okay? All right? If we do the more complicated example, so if we look at 1 plus y14 plus y14, y13, so again, this goes to e to the max of 0 minus t13 minus t13 t14 minus t14 minus t13 t14 t14 t13. Okay, same thing. Then it's easy to see that this thing is linear, but its domains of linearity are given by exactly that picture. Okay? So in this example, down here, T14 is negative, T13 is positive, so minus T14 is the biggest of all of these guys. Okay? So down here, this is minus T14. Here, everything is so negative that 0 is the max, and here, minus T14 minus T13 is the max of everyone. Okay? Okay, so we have a few ways of, we have a few things that we can associate with this picture of the Minkowski sum. There's the fan associated with each one. There are these polynomials associated with each summand. And there's the tropicalization of the polynomials associated with each summand. Okay, so these are sort of three natural things that we can associate with these summands. And these last points, the polynomials and these tropicalizations, turn out to directly connect these pictures to amplitudes. Okay? And in fact, let me just write down the amplitudes that they are associated with. This guy's. Sorry. So if I begin with the polynomials, I write down an integral. So this is, I'm going to call this A5. It's going to be a 5-point amplitudes, but we'll interpret in a second. First, I write down an integral from 0 to infinity with a form that's one of these sort of infamous, by now, d-log forms. Okay, so our form is going to be a d-log form on y13 and y14. Okay, so y13 and y14 are the sort of variables here. Now, this integral by itself is divergent, obviously, very divergent, right? It's logarithmically divergent at 0 and infinity. So we're going to repair this integral to make it finite. What we're going to do, in the neighborhood of 0, they're going to be factors that are powers of y13. So y13 is going to go to some power. What power could it be? Well, the most natural thing is the x that goes along with y13. And y14 will be raised to the x14. Right? We have now successfully repaired the singularities near the y's equals 0. But now these things are going to diverge as y goes to infinity. If the x's are positive, we fix things near x equals 0. Now they're going to diverge as they go off to infinity, right? So to make them die at infinity, there have to be some other factors that are going to suppress things at infinity, okay? But in our problem, we now have 3 interesting polynomials at our disposal. Right? We have these polynomials associated with the summands. So we're just going to write them down. We have the polynomial 1 plus y14. Okay, but remember, if we go back to the picture that Carolina drew, this mesh, this was associated with that summand that was anchored to this mesh point. Okay? So we're going to write 1 plus y14 to the power of the mesh that goes along with it, to the power of negative c24. This guy was this one, so we're going to write down 1 plus y13 to the minus C13. And this was the triangle, so we're going to write down 1 plus y14 plus y14, y13 to the negative C14. Okay? Now notice that if the c's are positive and the x's are positive, this manifestly converges. Just mindlessly converges, right? Because we've saved it near x equals 0. Well, actually, sorry. Doesn't so mindlessly converge. We've saved it near x equals 0. It has a chance to be saved near y goes to infinity. But obviously these c's can't be, for example, 10 to the minus 100 if the x's are 10. Okay, so the x's have to have some positivity property relative to the c's in order to ensure that this converges everywhere. Okay? And you can very easily check in this example, and it's true on very general grounds, that it's precisely when x lies inside the pentagon as defined by these mesh equations that this integral is convergent. Okay? All right, so the integral is nicely convergent. We have to have the x's are positive, the c's are positive. On top of that, we have to have x plus x minus x, all of that stuff. Okay, then the integral is convergent. Now, this object, yes.
Is the statement that if you move anywhere slightly away, it will diverge, or that this is a one positive?
No. It'll diverge. I mean, these integrals will diverge if you're outside the polytope. They'll just diverge. So the sort of polytope is literally the same as the domain of convergence of the integrals. Okay. Okay, now this is a slightly fancy-looking object. Okay, this is a slightly fancy-looking object. In fact, the x's have units. They're momentum squared. So to make this a unitless statement, I need to put something here that has units of 1 over momentum squared or length squared. So these things typically are called alpha prime. So alpha prime is just something there to make this have correct units. But we'll talk about it in a little bit more detail later. But this is, in fact, the 5-particle string theory amplitude. Okay? Right. So it has this interesting extra parameter alpha prime in it. This is a very interesting function of the x's. This is a quite complicated function of x's. It's meromorphic. So there's a lot to say about string amplitudes we'll not be talking about in this lecture. But what I just wanted you to see very quickly right away is that starting from the picture of the association of the Minkowski sum is about string theory. Okay? It's the Minkowski sum picture that immediately tells you how to write down a string amplitude. You just take the summands and shove them to the power of what appears in front of them. All right? And this is something that is going to give you string amplitudes. Okay? Now, we can ask what happens to these functions in the limit where the x's, where this combination alpha prime x is tiny. Okay? So alpha prime has units of a length. So saying that alpha prime x length squared, so saying that alpha prime x is tiny is the same as saying the momenta are very small. Okay? So this would be a low energy limit. If you're a string theorist, you would say that in string theory we have the particles that we see, and then there's massive cousins, string excitations of these particles whose mass is set by that parameter alpha prime. If you go to very high energies, you'll see all of them. Very short distances, you'll see the little wiggling strings. But at very low energies and very long distances, you're not going to see them, and you're just going to go back to seeing the good old-fashioned particles. Okay? So how can we study the very low energy limit of this amplitude? Well, clearly, as alpha prime goes to 0, this amplitude is actually going to blow up. It's going to blow up at some power of 1 over alpha prime. After all, the whole point of those exponents was to regulate these integrals. Okay? In fact, if we look at this integral, it would naively go like 1 over alpha prime squared, right? Because there's going to be a sort of a 1 over alpha prime from every one of these integrations. Conventionally, for that reason, sometimes people multiply this by an alpha prime squared out in front, just so we have something which is well defined as alpha prime goes to 0. But regardless of that cosmetic thing, it's going to be dominated when alpha prime is small. This is going to be dominated by the extreme regions in this y space, either when the y's go to 0 or the y's go to infinity, precisely because we're barely regulating it. Okay? So that's why as alpha prime goes to 0, So this is a string of alpha prime. But as alpha prime goes to 0, a string of alpha prime is going to descend to a field theory or particle theory, which doesn't have an alpha prime in it. Okay. And what does that descension look like? Well, I mean, if I go back to this integral, and I use these variables where y13 is e to the minus t13, y14 is e to the minus t14, then this is the integral over all t, so integral dt13, dt14, okay? The y13 to the minus x13 is going to look like e to the minus, I'm going to now put alpha prime to 1 now, since it's going to look like e to the minus t13 x13, e to the minus t14 x14, and then e to the minus c13 max of 0 and minus t13. E to the minus c24 max of 0 and minus t14, and then our favorite big guy, e to the max c14, 0, minus t14, minus t14, minus t13. Sorry for the small writing here, right? So this is what the field theory amplitude becomes. I mean, well, sorry, this is the full amplitude. I haven't taken any limit here, right? This is the full amplitude. I apologize. This is just the full amplitude. But now the point is that that in the limit that we're talking about, this integral will be dominated by the t's going to infinity. Okay? Oh, I'm sorry. No, this is the limit. Sorry. In taking the limit, the integral is dominated by where t's go to infinity, and where the t's go to infinity, we precisely replace the polynomials by these e to their tropicalizations. All right? So this is a different expression than the expression that I wrote down to begin with. The string amplitude is some sort of fancy curvy integral, right, with polynomials and so on in it. This is a simpler integral, right? Again, now what's inside the exponential is piecewise linear. It's not linear, but is piecewise linear. Okay? Is this clear so far? Any questions about this? So this is what the low energy field theory limit looks like.
I think before you integrated from 0 to infinity, now it's minus infinity to
infinity. Oh, because this was in the language of the y's. So the y's are from 0 to infinity, so the t's are from minus infinity to infinity. Okay? So the t's are from minus infinity to infinity. Okay? And now this integral actually has a very beautiful interpretation. Okay? Because exactly what we said before, remember, what we said before is that each one of those factors, so let's try to do this integral. Well, obviously, the integral should be easy in some local region in t space, because each one of these factors is just going to turn into something linear. Okay? So let's just see where each one of them is linear, right? So where was this guy linear? So this part of that part of the exponential looks like this. That part is going to look like what we figured out before. So it's going to look like c14 times minus t14 here, right? It's going to look like c14 times minus t14 minus t13 here, and it's going to look like 0 here, c14 times 0. Okay? So that's that factor. What about this factor? Well, that's piecewise linear in another region. In fact, to see it, well, it by alone, oops, that red thing disintegrated. So remember, this factor alone was piecewise linear, like in this region. And obviously, when t13 is positive, so I would add to this plus c13 times 0. And when t13 is negative on this side, I would add to it plus c13 times negative t13. And similarly, for the last guy, well, I'll draw it the same color here, right? For the last guy, then down here I would have plus C24 times negative T14, sorry. And up here I have plus C24 times 0. Okay? Oh, sorry, and I didn't write. I should have written things here. So, no, sorry. Yeah, this is okay. So, but I should have remembered this C14 minus T14 minus T13 was valid in this whole region. Okay. So in this little corner, sorry, I did it precisely wrong. So from C13 I have 0 on this side, but I have negative C13 T13 on this side. So here I'm going to get C14 times negative T14 and negative T13, and then plus C13 times negative T13. Okay, and so on. Okay, okay. So now I have the whole plane is divided up into these 5 regions that we get by putting all the fans on top of each other. And in each one of these regions, the integral is linear. Okay? So we can do the integral. Now, the integral is easiest to do in this region. Okay? And I may have screwed something up here. Sorry. Oh, sorry, I precisely screwed up. I screwed up at the very beginning. Someone should have stopped me. Sorry. I screwed up in writing this expression. Okay? Okay, so if we have this guy, okay, here is negative T14, okay, but here is 0. Okay, because it was max of 0. This was max of 0 and negative T13 and negative T13, negative T14, negative T13. Okay, so that's 0 here, and here it's negative T14, negative T13. Okay, sorry. Okay, so very good. So we erase that here, but now we have to concomitantly erase it here, and here is where I should have this negative T14, negative T13. Okay. Okay. Anyway, so you see you have an expression that's piecewise linear in each one of these cones, and now let's look at what it looks like, for example, in this cone. This is the simplest one in which we can do it, right? So in that cone, what are we getting? In that cone, we're getting the integral 0 to infinity we're getting the integral 0 to infinity from this cone of just dt13, dt14, e to the minus x13, t13, e to the minus x14, t14, all the c's go away, and this is just equal to 1 over x13, 1 over x14. Right? And that's precisely the Feynman diagram that you'd associate with having these two chords, x13 and x14. Right? That's exactly the Feynman rule that we'd associate with that.
Okay. Sorry, why did all the c's go away?
Because in this region, the contribution from the c's was 0.
Okay, yeah.
Okay, and so we always have the x13, t13, x14, t14 on top of what I added. I should have added that even there, but that would just be common linear factor everywhere. Okay, yes?
Why did we change the boundaries from minus infinity to 0?
Because here, this is only in this cone. See, now I'm going to do the integral. I want to do the integral over all t's, but now I've simplified my life to see that in this cone it's linear. In this cone it's linear. In each one of these 5 cones it is linear. And so I'm just going to do the integral over each cone at once. Okay? In every cone it's linear, and this is the easiest cone in which I can do it, and what I get is 1 over x13, x14. Now, physicists call this trick for representing 1 over x equals the integral 0 to infinity dt e to the minus tx. This is called Schwinger parametrization. Okay? There's various nice physics words associated with it. You can sort of think about t as a length of a propagator in position space. Okay? So there's various nice words associated with it. But it's just a way of representing these propagators. So what we've seen is that in this cone, I get something that looks like the Schwinger parameterization for that diagram, right? So the cone goes with, that cone is associated with that diagram. And when we do this integral, what we're getting is the Schwinger parameterization for that diagram. And the contribution from that cone is precisely giving me the Feynman diagram associated with that, with the corresponding, the integration over the cone is giving me the amplitude that I'll get from the contribution of the amplitude from the corresponding Feynman diagram. You can easily check that the same thing is true for all of the other cones. Okay? It's maybe slightly interesting, like these cones don't look like the standard positive cone for that formula to be valid, but of course you can always do a linear transformation. You know, the integral over this cone, I can just do a linear transformation to bring it to the standard form, which is the positive quadrant. The integral over this little triangle, I can do a linear transformation to bring it to a positive quadrant. And every one of those contributions ends up being 1 over x from the corresponding diagrams. Okay? Okay, so let's just pause and say what has happened. We have this picture of the isosahedron. We haven't, well, Carolina gave you a picture of where it came from. We're now gonna talk about where it comes from in a more sort of primitive, principled way. But imagine you got the picture. The really magical things that is presented as a Minkowski sum. In the language of the polytope or in the language of the fan, that we have a fan that has cones that cover all of space. Okay? Every cone is associated with a particular triangulation, a particular diagram. Now, that's already interesting. That's already interesting that there's some way to divide all of space naturally so that into cones where each cone corresponds to a diagram. That already sounds like progress. Okay? But having done that, if someone told you, well, then go add up the Schwinger parameterizations from every diagram, you'd be, oh, this still sucks, because I still have to go cone by cone by cone, Schwinger parameterize for each one, and add them all up. That's basically doing Feynman diagrams again. But the fact that this sort of complicated set of cones is secretly a simple set of individual fans put on top of each other tells you that there is a simple piecewise linear tropical function that produces all this complicated mass of the Feynman diagrams. Okay? Now, this small example was maybe not small, is maybe too small to impress, but it already illustrates the point. There are 5 diagrams. We have 3 tropical functions. Okay? We did not have one function for every diagram. Instead, it's the magic of the Minkowski sum picture, right? That it was presented with these sort of 3 simple fans on top of each other. So 3 tropical functions were all you needed to produce the 5 diagrams. Now, what's going to happen in general, and that's what we're now going to see, is that not just at tree level, but when we generalize to all loop orders, all surfaces, etc., these 2 bits of magic always happen. So first, there's a way of getting into the space of the appropriate dimension and seeing that it's naturally divided up into cones. And each cone corresponds to a diagram. But you don't manually have to sort of, make them. It's just going to come out of the box. We're going to figure out how to hand you a bunch of vectors such that the cones made out of them are automatically going to correspond to diagrams. That's going to be small miracle 1. Bigger miracle 2 is that there are some functions associated to these pictures as well. There are polynomials, as we saw here, and there are tropicalizations. Okay? So they both have an interesting role to play. These are going to be few of these polynomials. So just give you just so you have an example in mind, if we're talking about tree amplitudes, asymptotically the number of Feynman diagrams, the number of triangulations are given by Catalan numbers. And Catalan numbers grow like 4 to the n if you have an n-gon. Okay, so the number of Feynman diagrams are growing exponentially. However, we're going to give about n squared tropical functions. We're going to give about n squared polynomials. there's going to be a polynomial associated essentially with every point in that mesh, right? Or there's going to be a polynomial associated with every one of these xij's, and every one of these ij's there's going to be a polynomial, and the polynomial will have at most n terms in it. Okay, so I'm going to hand you around n squared polynomials, each one having at most n terms. All right? No 4 to the n here. So clearly I'm not summing over all diagrams, right? The sort of magic is I'm going to give you n squared polynomials with about n terms each. First of all, if you shove those polynomials in to the integral dy over y to the x, product of all the polynomials, so they're minus c, that will define string amplitudes. Okay? Without your string theory course. And secondly, if you tropicalize those expressions in just the way that we talked about, that will give you a global Schwinger parameterization for all the diagrams together at once. Okay? But again, the magic is there will be order n squared tropical functions, each one of which has a max of order at most n things. Very small number, but if you put them all on top of each other, the domains of linearity of all of these guys exponentiate, right? And generate this humongous complexity of all the diagrams together, right? This is the second magical fact, a more magical fact. Both the existence of the polynomials and the existence of, and the fact that, well, anyway, the existence of the polynomials is the essential fact, and their tropicalization is this sort of, as this very beautiful interpretation, as giving you cone by cone the Schwinger parameterizations for each diagram, but in a global way that combines them all together, okay? The point is that these piecewise linear functions morph into the Schwinger parameterization for every diagram as you move around the cones without doing any manual work, right? And it's literally this difference between polynomial versus exponential complexity. Sort of polynomial complexity in, exponential complexity out. All right, so those are the things that I now want to explain, where these things come from. Before doing that, let me mention a final thing that we can see in this example. Okay, final thing we can see in this example. That's also going to play a sort of starring role. And this is the existence of something that I'll give some whimsical names to, and then an official name to. But let me start with the more whimsical name. Remember, part of what the isosahedron does is, if we drew this picture, of course it captures all of the compatible chords and so on. But a sort of very minimal thing that it does is it keeps apart things that cannot cross, right? That's the point, that we can't have 1, 3 and 2, 5, they cannot occur together, right? The chords cross. The chords 1, 3 and 2, 5 cross. And so part of the job of the isosahedron is to keep them apart, right? So 1, 3 and 2, 5 do not meet. Okay, 3, 5 and 1, 4 cross, so 3, 5 and 1, 4 do not meet. Okay. Of course, it does more. The things that do meet have the correct combinatorial. They all meet the way they should and so on, but the most zeroth order thing that it does is keep things apart. That's very beautiful that we can do that in this sort of polytopic way. But you also notice that it's kind of, it's not entirely rigid, right? I mean, of course, it can move these faces around parallel to each other in various ways. So it's not entirely God-given, okay? There is a more God-given object, which does exactly the same thing, that you can call, these are the whimsical words, you can call a curvy isosahedron. We sometimes call binary geometry. And okay, it's also positive coordinates for Tech-Müller space, but I fall asleep by the middle of that sentence. Okay, so so it's related to compactifications of Tech-Müller space in some way, but if you don't know what that is, that's more than fine by me. Okay, so So what is this doing? So there is something interesting here. Remember, what the conventional sort of flat associahedron, this is polytopic, this is cut out by linear equations. What the conventional flat associahedron is doing, amongst other things, is keeping things apart. And so we do that by, well, we associate these variables x's with them and so on, right? So the flat associahedron, and on this side, the flat associahedron for every, so our, we have chords. We have some chords ij, other chords kl. They want to be kept apart from each other when they cross and so on. In the flat associahedron, we associate these things with variables xij, and then there's the associahedron as a polytope. That's cut out by equations involving these x's. So this is the flat associahedron world. In the curvy world, or nonlinear world, every one of these chords is associated with another variable we call uij. Okay? But we're not going to write down inequalities and things like that for them. Instead, these uij's are going to satisfy the following set of very interesting nonlinear equations. Uij plus the product over all chords kl Now I'm just writing these equations down. Okay? Well, again, we'll understand better where these things come from. Okay? But let's say just out of the box, I handed you an equation that looks like this. Well, what's your first reaction to this equation? Let's try writing it down at 5 points. Okay, so at 5 points, very simple. At 5 points, we have that, so let's draw our 5 gone. So I have like the equation for U13. So U13 plus the product of all the chords that cross 1, 3. So who are the chords that cross 1, 3? There's 2, 4, and 2, 5. Those are the only ones that cross 1, 3. So U13 plus U24, U25 is equal to 1. Okay? And then we have the cyclic friends of this guy, right? So we have plus U24 plus U35, U13 equals 1, and so on. Okay, so we have a total of 5 equations. Okay? So without thinking, you think you have 5 equations, 5 unknowns. This has some solutions in points. Okay? The interesting thing is it doesn't have solutions in points. It has a full 2-dimensional space of solutions. Okay? These equations have a full, interesting 2-dimensional space of solutions. For example, a natural thing you could do, this turns out not to generalize very easily. Okay? But one thing you could do in this example is to just choose 2 of the u's and solve for the rest of the u's in terms of them. For example, you can find that U25 is 1 minus U13, U14. If you just solve these equations, U35 is 1 minus U14 over 1 minus U13, U14. And U24 is 1 minus U13 over 1 minus U13, U14. Okay, so this is one way you could solve the equations. All right, you can just check that that's true. All right. But what's interesting about these nonlinear equations? Why do we call it a curvy association or binary geometries? What's that word binary? Again, it has to do with the word positivity, because we ask for real positive solutions of these equations. Okay? So I'm going to ask for what happens when the uij are greater than or equal to 0. What happens if the uij are greater than or equal to 0? These equations then tell us, not just these, but in general, remember, we're writing down uij plus the product over kl of ukl is equal to 1, right? So these equations are telling us that if the u's are positive, if the sum of 2 positive numbers adds up to 1, they all also have to be less than 1. All right? So all these u's have also got to be less than or equal to 1. Okay? That's where the word binary comes in. And now they have an interesting property. Suppose a given u, like a given u I star j star, some u I star j star. Let's say this heads to a boundary of the space where this goes to 0. By the dint of these equations, all of the u's that cross it must go to 1. Okay? So the UKL for KL crossing I star j star have to go to 1. Okay? That's remarkable. If you think about hitting the boundaries of the space corresponding to some u's go to 0, you see this is doing exactly what the isosahedron is doing. It's keeping apart things that cross. But it's keeping them apart in an entirely rigid way. There isn't any parameters that you can move around. These variables are from 0 to 1. And when you go to a boundary for one chord, all of the chords that cross it just go to 1. Okay? All right? Okay, so now this turns out to exist. These variables exist at tree level for the case that we're talking about. Again, all of this generalizes to all surfaces in interesting ways. You draw any surface. There is a chord. There's a variable associated with any open curve on the surface. And you write down in general, if you have a curve x on the surface, you write down this formula, the product over all other curves of the u for the y, and it's raised in general to the number of times the curves x and y intersect each other. Okay, so that's just a sneak peek. That's the equation. It's a sneak peek because I like to say if I had to hand someone one fact and tell them to go to a desert island and work out what I did for the last 5 years of my life, that would be what I would do. Just hand them that equation, say go, right? And then just studying that equation would lead to all the things that we're about to talk about. All of it is in understanding how that equation can be true and how to solve it. Okay, we'll see how much we get to this later in this lecture. But so it's true not just at tree level, it's true for all surfaces. But what's especially interesting about it is we know how to solve them. Okay? There's a way of solving these equations, and the u's are given as ratios of polynomials. Right? So let me tell you what this ratio of polynomials looks like for our pentagon example. For instance, we find that u's are parametrized in terms of some positive coordinates y. Okay? And the formulas are that u13 is y13 over 1 plus y13. u14 Okay, and I just invite you as a little exercise to check that these satisfy u plus uu equals 1. Okay? So for instance, if we take u13 plus u24, u25, okay, this is u13 is y13 over 1 plus y13. But u24, u25, there's a nice telescopic cancellation of that factor and this factor, and we're left with 1 over 1 plus y13. And this is dutifully equal to 1. Okay? So you see, we're solving these u equations. We're solving these u equations in terms of these interesting polynomials. Now notice those are exactly the polynomials that showed up in our previous picture. Okay? They're precisely the polynomials that showed up in our Minkowski summaries. So let's summarize what we saw in this example that we're now going to give a rational explanation for. Okay, we started with the isosahedron. The simple case, there was a pentagon. we drew the dual fan associated with it. The fan has the feature that it divides the space up into cones. Every cone corresponds to a triangulation or a diagram. Okay? The fact that the association has a Minkowski sum decomposition is reflected in the fact that the fan, even though it has 5 pieces, is naturally thought of as sort of putting 3 simpler pieces on top of each other. And that 3 versus 5 distinction gets much more dramatic at higher points. Okay? There is a small number of pieces, each one of which looks like the fan of a simplex, which when you put them on top of each other, order n squared pieces, where you put them on top of each other, generates the horrendous complexity of all the 4 to the n Feynman diagrams. Okay? There is this simple integral that you write down, just integrating with the d log form in the, so if we can then associate polynomials with each one of these summands. There's a simple integral that we can write down with the d log form. Y to the x and all the polynomials raised to the power of their coefficients in the summand that gives us the string amplitude. If we take the low energy limit of this, we simply tropicalize this integral, and that's interpreted as the global Schwinger parameterization, a way of combining all the Feynman diagrams together in a single object, so that cone by cone we get the contribution from the diagram, but without having to invent the diagrams, right? They all sort of come out. And these polynomials themselves are associated with this interesting notion of a binary geometry, this much more rigid way of associating a geometric object with the combinatorics of triangulations of an n-gon. Okay? There's a sort of curvy version of the isosahedron where there's no moduli, there's no parameters, it's just zeros and ones, right? But with every variable you associate a u, this interesting u equations, which have the feature that when you approach boundaries, the u's go with u's go to 0, all the crossing chords go to 1. In fact, I'll mention one last thing here to just close this example. I'm going to go back and write the string amplitude again. Remember, the string amplitude was written in terms of these polynomials. But the u's are some interesting, just combinations of these polynomials upstairs and downstairs. So I'm going to go back and I'm going to write the string amplitude directly in terms of these u's, where they look much more elegant. So that string amplitude, again, is still this d log form. It's still the integral 0 to infinity dy13 over y13, dy14 over y14. Okay? But all of the rest of the stuff that we had before just turns into the product over all chords uij, the u variable to the power of xij. That's what the string amplitude is. Okay? See, this is a much more elegant form. Okay? This form makes a number of things obvious. In fact, it makes all the qualitative and quantitative features of the amplitude obvious. For example, it makes it obvious that the only singularities, again, this is a d-log form. A sort of cool thing is to show that this is a d-log form that has logarithmic singularities everywhere the u's and any of the u's go to 0. Okay? That's a small extra step that's not hard to prove, but just by that. Okay? So anywhere, so this integral is only going to develop singularities in the neighborhood where some u's go to 0. That might be at 0 or infinity and y, it doesn't matter. Sort of invariantly, it's only developing singularities as the u's go to 0. So what's rescuing it is its power, right? So that's why we're going to have poles that look like 1 over xij as some of the xij's go to 0. Okay, so that's the sort of first thing which is obvious. That was our locality, right? Where are the poles where the x's go to 0? Okay, we're seeing that. Okay, so we're going to have a pole as xij goes to 0. As some xij go to 0, this amplitude will go like 1 over xij. Okay, but now comes the real magic. What happens to this factor at a given xij goes to 0? Let's say given, again, xi star j star goes to 0. Let's imagine drawing a big n-gon. This is going to be true for any n. Right, so let's imagine here's my chord I star j star, and this xij is going to 0. That means that this integral is being localized in the neighborhood of where the corresponding u I star j star goes to 0. So what happens to this factor? Right? Well, we're going to pull out of it some u I star j star to the x I star j star. That's a factor that's coming out of all of this. That's in fact exactly the factor that's getting slightly rescued by the non-zero x to give me something that's going to be 1 over x and is getting regulated, right? That's my pull. But what about everything else? Well, notice this chord divides the n-gon naturally into a left part and the right part. But all of the u's that correspond to chords crossing here are going to 1. Right? That's the point. When a u goes to 0, all the chords that cross it go to 1. So in this product, all of the pieces that are a u to the power of x corresponding to something that crosses are going to 1. So what we're left with is just this factor that pulls out times just a product over the left of u to the x left and a product over the right of u to the x right. This is factorization. This is precisely the phenomenon of factorization, okay? Because then it's very easy to see that this form also just splits. There's the part associated with that going to 0, and the rest of it splits into a product on the left and the right, and therefore the whole amplitude goes to this times the amplitude on the left and the amplitude on the right. And in fact, this has nothing to do with taking the low energy limit. This is a full exact property of the full string amplitude, which is one of the things that makes string theory consistent, okay, even beyond field theory, right? So I hope you see very vividly in this example the kind of abstract discussion from yesterday, right? We started with a picture. There's maybe Carolina started with a mesh, some funny wave equation in this mesh space. You get a polytope. You know, you're following your nose. I hope it's clear at no step are we cheating on looking at Feynman diagrams at the end of the book, right? There's nothing like that going on, okay? But then we're sort of, after a few steps, we're naturally led to this object. This object does everything that Feynman diagrams do, but without having any reference to particle trajectories or anything like that, okay? In fact, the sort of stars of the show here are variables associated with like chords in this n-gon, right? And remember, those chords in the n-gon are related to the kinematic variables. The kinematic variables are also associated with chords on the n-gon, right? Okay. All right. So, okay, let's pause now, and I'll ask if there's any questions. Yes.
So these u and y variables are
Yes.
they somehow related to some cluster variety?
They're related to they're related, but they're not precisely cluster variables. For a variety of reasons, surface cluster algebras are not quite what is needed in this story. They're close, but not exactly. Yes, they're more closely related. If you know, they're more closely related to Fock-Goncharov coordinates, but they're also not precisely that. Or there's a very special set of Fock-Goncharov coordinates that do this job. Okay, but part of the point of these lectures is to not assume that you know fancy things and just build it from the ground up. So in the next 50 minutes, we'll sort of see where these things come from the ground up. Yes. Super.
So you were speaking about how it is surprising that this tropical representation exists for the
Yes.
full amplitude in one Schwinger parameterization.
Yes.
So I wanted to ask, so suppose I start doing this. Instead of looking for positive geometry,
Yes.
I take some new theory, some different theory,
Yes.
and ask, does it have a global Schwinger parameterization?
Yes.
For example, I think Bruno has some papers where they have found global Schwinger parameterization, but in a different structure than
Yes, I think everywhere we have global Schwinger parameterization, there is some interesting positivity behind it. Okay, there are some positive parameterization, some set of polynomials that you can, in the end, interpret as giving you this picture of naturally a bunch of Minkowski summands that are summing up to a complicated geometry. That's the universal thing in all the examples that we see so far. And all the examples also have stringy integrals that go along with them. Okay, so there is extensions, Nick, Bruno, others have talked about CEGM theories and so on. The original motivation for those things came from the CHY formalism. But in fact, there's fully stringy versions of them. I mean, so it's not restricted to the field theory limit. And from my point of view, that's a more natural way of thinking about what they are. Okay, so that's
from the perspective of positive
Yes.
geometries, is
Yes.
there some qualitative difference in finding finding it through a positive geometry, or finding it, or are these just equivalent completely?
Well, I mean, all I can say is that I don't know what to say in general. Maybe here's a place to perhaps say it. So first of all, everything that I've been talking about here is in the context of the trace phi cube theory. Okay, so the only dependence is on simple scalar kinematics. And we have expressions that look like this. Like literally this expression, sorry, if we do this, this was meant to be a general n. So this would be some maybe dy13 up to dy1n. I'll say what this means in a moment. But anyway, some expression like this is true. And so you might think this is very special to the trace phi cube theory. Can you do this for trace phi to the 4 theory? No. Okay, there's nothing sort of huh? This is actually n minus 1. Thank you. Okay. You might think that anyway. Can we do it for trace phi to the 4 theory? Some other theory? No. Okay. So at least not in any obvious way. But one of the surprises of the past few years is that literally these functions just slightly reinterpreting what you mean by the x's. If we take the x's and just shift the x's in some simple linear way, take us from describing the amplitudes for trace phi cube, which is a dumb toy model that maybe none of us care about, to describing real-world particle physics. Okay, so you shift these amplitudes in one way, you shift these functions in one way. I literally mean shift. I mean doing nothing to them, just reinterpreting what you mean by x. Okay, you just shift x goes to x plus some constant depending on what I and j are, and then all of a sudden you have the amplitude for pions, which are some of the particles associated with the strong interactions. And if you do it literally in this way at finite alpha prime, and shift x by a single unit, x goes to x plus 1, x plus or minus 1 over alpha prime, then this thing turns into the scattering amplitude for gluons, real gluons. And unlike the story of the amplituhedron, this has nothing to do with supersymmetry. The words n equals 4, super Yang mills, etc. make no appearance. This is for totally non-supersymmetric gluons. And at loop order for totally non-supersymmetric gluons. Okay? These second two statements are a much bigger surprise, that somehow this seeming dumb toy model contains in it theories we care about a lot more. And actually some of the surprising properties that Carolina was mentioning this morning, that these amplitudes have surprising zeros, and they factorize in surprising ways in the neighborhoods of these zeros, they in fact port to all these other theories too. Okay, so the theory of pions and of gluons have exactly the same mysterious properties. That's actually how, with Carolina and Jen and friends, we were led to discover these things backwards. We ran into the zeros. Then we observed, just experimentally, the zeros were also there for other theories that we cared about more, which is very surprising. Why the hell? Those theories were not related to the association. We didn't think. Well, we were wrong. They are, right? It's exactly the same function, shifted in this interesting way, takes us between all these different theories. So this is maybe a kind of example of what you're saying. Had you told me ab initio ahead of time, take the diagrams for the nonlinear sigma model that describe pions and try to put them together in Schwinger parameterization, that's good luck, right? It's a total disaster. I would never try doing that in a million years. And I would also not think in a million years that all I have to do is go back to this example and do some stupid shift on the x's in order to get the right answer. Never mind that I could do the same thing for gluons, which is utterly shocking, right? That I would never thought. So somehow that's the nature of the beast in this business, is it does not commute with responsibility. I don't know how to say it, but you want to do something, say, oh, I'm going to take every Feynman diagram and figure out how to put the numerators in Schwinger parameterization, and then globally Schwinger parameterize it. People have tried to do that with some degree of success, but somehow it does not have the same remarkable, striking feature as what naturally comes out when you pursue what the mathematical objects want to do on their own terms. Okay, so that's why I don't have a general answer to give to your question. Okay, any other questions? Yes.
I didn't quite understand why when you set the xij to 0,
yes,
that also the uij went to 0.
Oh yes, because the point is, remember, if I didn't have this factor at all, this integral is very divergent. Okay, it's logarithmically divergent both on the y's go to 0 and they go to infinity. Okay. What this factor is, now it turns out that the y's go into 0 and infinity. In fact, where this form has a logarithmic divergence is in one-to-one correspondence with where the u's vanish. Okay, so where this thing develops a logarithmic singularity are where the u's vanish. Now the x's are there to ensure that you nonetheless get something finite, right? It's like integral, sorry, maybe I should have said this, but this is just saying, you know, integral 0 to whatever dy over y is log 0 is infinite, but dy over y to the a is 1 over a plus dot dot dot, right? So just the point is that these little exponents save the integral, right? They make it convergent, but as that exponent goes to 0, this integral develops a pole. Okay? So if we go back here, if a given xij goes to 0, there's a region in this space that's going to have a logarithmic divergence when the u goes to 0, when the u for it goes to 0. Okay? If the xij is not quite 0, the amplitude will be dominated by this neighborhood. It'll get a factor of 1 over xij, and the rest of the integral will be what you get from the other parts of the integration in the neighborhood of where that u goes to 0. And because of this sort of magic fact that as a given u goes to 0, all the u's that cross it go to 1, the rest of the integral just dutifully factorizes. Okay? So what you're left with is just the product on the left and the product on the right. Okay? I want to stress again, this is qualitatively different from where factorization comes from with the picture of space-time processes and Feynman diagrams. Okay? And this qualitative difference is related to what may have seemed like a sort of too vague remark yesterday, that it's the two-ness of the pi dot pj versus the oneness of the pi's that matter. See, the Feynman diagrams are all about oneness. You know, you have a bunch of momenta coming in, you're keeping track of the momenta of the particles, then there's a propagator that's the sum of all those momenta, and it goes from here to there, right? So that's how Feynman diagrams make manifest that singularities are associated with propagators. This picture does not ever see single indices. This picture is all about pairs. From the beginning, it's all about pairs. It's about curves on the surface. It's all about pairs. And therefore, the way it manifests factorization looks nothing like a particle propagating and going on shell and cutting the picture. It's just something totally different. It's this binary geometry. Okay? And that's, again, a concrete instantiation of this general fact we've seen over and over in this business of the existence of natural geometric objects that factorize on the boundaries for their own private reasons, which don't, on the face of it, have anything to do with particles going on shell in space-time. Okay? Okay, any other questions? Yes?
In terms of complexity reduction,
yes.
So from going to 4 to the n diagrams to
yes,
n
yes.
squared, do you somehow know that this is the best you can do?
I would be surprised if you could do better, but I'm not sure. Yeah, I mean, it would be very interesting. It would be, and just to maybe make a point, whether we get there or not, I hope now you can see why this way of thinking offers some hope for asking what happens when the number of particles goes to infinity. Okay? Because we're going to have an integral of something which is e to the minus some piecewise linear expression, which is not that complicated. It's a sum of sort of n squared pieces, each one of which is the max of things that involve order n things. Of course, we're doing an order n dimensional integral, but it's a single integral. It's a single integral over one space that somehow something nice should happen in the large n limit. Okay? So that's not insane that something like that should happen. And in a very precise sense, what happens is that these piecewise linear things smooth out. And that the large n limit is a much smoother object than you would naively think from putting all these maxes on top of each other. That smoothing phenomenon is a very interesting one, which if we get to it tomorrow, we'll talk about. All right, so I have 40 minutes. 40 minutes? That's challenging, but let's see what we can do. So now I want to tell you where these things come from. Now, first off, we're going to go back to this picture where we sort of think that we have a scattering process, but we already learned, let's go back to the case of the pentagon, that we can think about this 5-particle tree amplitude in terms of triangulations of a 5-gon or an n-gon in general. Okay? And the kind of first way was the way that Carolina mentioned in her talk, that we could sort of draw a dual of this triangulation, and the dual of the triangulation looks like the diagram that we have talked about. There's a closely related way of thinking about this, which is somehow deeper. And this has to do with going all the way back to these being colored particles. Okay? And in our 3 discussions of color today, only at the very, very end did the following picture show up, which I'm glad it eventually showed up. Okay? So we're talking about this trace phi cube theory. The phi is a matrix. This is the point. Phi is a matrix. So we imagine the phi is an n by n matrix. It has an upstairs and a downstairs index. So when we write phi cubed, we really mean phi AB, phi BC, phi CA with Einstein summation convention, sort of summing over all these things. And so it's convenient to keep track of what these indices are with a double arrow notation. Okay, so if I have something like this, the upstairs arrow will be, arrow going this way will be a j, the downstairs arrow will be an I. Right? And so when I write trace phi cubed looks something like this. So this will be, let's say, an I, but the fact that it's a trace means that this index is identified with that one. Okay, so this I survives out to here, and this j survives to here, and this k survives to there. Okay? Okay? So how would I draw a 4-point diagram? You would draw it like this. This is the fat graph, or ribbon graph that Sergio was referring to. Okay? That's one fat graph. This is another fat graph for the other diagram that I would draw. Okay? Okay. And if I had a loop diagram, you know, diagrams that like you saw in Ruth's talk, a diagram like that, when the particles have color, would look like this. Okay, everything just gets fattened out. Okay. Okay, now, there's 2 very closely related points, very simple, ancient, very well appreciated. But let's just say them, they're very slightly different. One of them is that we can think of each one of these diagrams as being drawn on some surface. Okay? So for example, we can think of the tree diagrams as being drawn on the plane, you know, then ordering for the external lines without any crossing lines. Okay? That's one picture we can think of as being drawn on a plane. The other one is that we can think of every one of these diagrams as actually defining a surface. They're 2 slightly different ideas. Okay? So for example, this diagram is going to define a surface which is a disk with 4 marked points. 1, 2, 3, 4. Okay? So how does this correspondence work? Well, how would you define a surface? You can define a surface by getting a triangulation of the surface. Okay? So what is a triangulation? It's a collection of triangles with an orientation, right? And they're supposed to at most meet on common boundaries with opposite orientation, right? So we're talking about orientable surfaces here. So I could give you the triangle 1, 2, 3 and the triangle 1, 3, 4, and those triangles give one definition of this surface. Okay? A ribbon graph like this, a fat graph like this, is giving you exactly the same data. Okay? You can think of each one of these vertices. You can think about the roads coming in as being the edges of the graph. Sorry, the edges of the triangles. And the triangles that meet along common boundaries are precisely the things that are joined by these propagators. Okay? So this picture, where now I would call this like color 1. This is color 1. So since it's color 1 everywhere here, I'll sort of just draw 1 underneath here everywhere. It's like there's a region 1 here that goes along with that line. There's a region 2 that goes with this line, 3 that goes with this line, 4 that goes with this line, and so on. Right? This picture is defining this triangulation of the surface. And we can see this now in various ways. But instead of drawing sort of dual diagrams, you can just think about what happens to this picture if you shrink the black regions to points. If you shrink the black regions to point here, that black region turns into this marked point on the outside. This black region turns to this marked point on the outside, and so on. Okay? Is that clear?
Sorry, black means now the white shade.
Yeah, I'm sorry.
Okay.
This is the usual blackboard problem. Yes, this is black. Sorry, I apologize. Yeah, yes. This white-black region. Anyway, this region, you shrink it, turns into that one, right? And I'll leave it for you to have fun to see, how you can, anyway, just interpret every aspect of this picture here. But again, the idea is that this vertex is a triangle, okay? This vertex is a triangle, and they're meeting along common boundaries, okay? So notice two different things. One of them is that all the diagrams can be drawn on the surface. The other one is that any one diagram defines the surface, okay? So when we say we're summing over all triangulations, right, you first have to tell me what surface I'm talking about, then I'm summing over all triangulations of the surface, okay? And so I'm going to pick one diagram to define the surface. I'm not going to draw all the diagrams, I know one diagram to draw the surface. I want to emphasize this is not even a Feynman diagram, we're not computing anything with it, it's just representing, if you like, nothing other than the flow of color. Right? These pictures are just about the sort of flow of color, which tells you what defines the surface. Okay? So I'm going to choose one diagram to define my surface. Okay? So let's do that. And now we're going to work with the 5-point example again. Right?
So I have a quick question.
Yes.
So does the genus in the second law not play any role here? That we have a genus 1?
Very much so. Yes, yes. So in fact, the thing that Qingling mentioned, maybe I'll give you an example here. Okay. So let's look at this example. So this has 4 lines sticking out of it, and let's look at another example. Oops, very bad at drawing. This also has 4 lines sticking out of it, okay? These are 2 diagrams that have 4 lines sticking out of it. This is the triangulation of a surface that has 4 marked points on the outside and a little hole in the middle. Sometimes the hole is called a puncture, okay? Is that clear? So if this is region, 1, 2, 3, 4, this would be, again, 1, 2, 3, 4, and this would correspond to sort of this kind of triangulation of the surface. Okay. What about this guy? This guy is a triangulation of an annulus. This is an annulus with 3 things on the outside, 3 marked points on the outside, and 1 marked point on the inside. If you don't see that immediately, I'll leave that as a little exercise for you to play with. Okay, so this color line 4 going around, this region 4, you see, this is color line 4, so this whole region shrunk to a point is giving me that guy. So this would be 4 with 1, 2, 3, let's say. Okay. Okay, and this is also, it's not literally this one, but it'll look something like this. I don't know, some triangulation that looks like that. Right? So this is a triangulation of the surface. But now, remember, we're supposed to. All of these lines have color. So the color here is specified by the external color. Red. Red, stays red, goes red. Blue, stays blue, goes out here, right? But in this loop, I don't know what the color is. It can be any color. So I should sum over all of the colors. And that's why the final answer here is proportional to the number of colors, n. Okay? So this is a planar diagram, and it's proportional to the number of colors, n. This diagram has all the colors are also determined. Right? Red on the outside, blue, green, cyan on the inside. All the colors are determined. There is no n. So this is the simplest example to see that the planar diagram is more enhanced by powers of n than the non-planar one. Okay? And that's a special case. You can have fun drawing 2 3-points. Draw something like this. A 3-point on one side, 3-point on the other, and you can either join them up straight across, that's one diagram, or you can join them up like a pretzel, that's another diagram. This one's a torus. The first one is just a sphere with 3 punctures. And the first one, the sphere with 3 punctures is proportional to n squared. This has no ends. The color line just goes around once. Okay? And so, again, there's just one power of n. The other one has three powers of n, so it's enhanced by another factor of n squared. In general, the powers of n are given by the Euler characteristic. So that's where the genus comes from, and that's why if you send the number of colors to infinity, the physics gets dominated by planar graphs. Okay? So that's one reason physicists care about the planar limit. But nothing in this story depends on that fact. Okay, so we can do things planar, non-planar. It doesn't make any difference. Okay, now let's continue. So we're going to draw we're going to do that 5-point tree, and I'm going to choose my representative graph. Just to be the sort of obvious, keep running out of chalk here. Oh, here's some more chalk. Oh, it's not white. Oh, there's some white. No, there's some white chalk here. It's fine. It's good. Okay, so let's take this is our surface. And this is going to be, we have this triangulation. That was the one that Carolina was also talking about. And that corresponds to this fact graph. Okay, again, let's see why. This triangle 1, 2, 2, 3, 1, 3 is this vertex here. And this is the road 1, 2. See, 1, 2 is 1, 2. 2, 3 is 2, 3. And 1, 3 is 1, 3, right? So this vertex corresponds to this triangle. This vertex corresponds to this triangle. This vertex corresponds to that triangle, okay? So having picked your parent, base fact graph to define the surface, we're done, okay? In the sense that our world is now fixed. From now on, we're going to live in the world of this fact graph. Not going to talk about surfaces, we're not going to talk about everything else. Our entire universe is living inside these graphs. All right? So in particular, when I go back to this picture, I say, but what about all the other triangulations, Feynman diagrams, all the rest of them? We're supposed to sum over all the triangulations of this graph, right? How do I think about the other triangulations if I'm not allowed to look at this picture? I only can look at this picture, okay? So that's what we're going to just learn to do now. Just take a second and learn, how do I think about all the curves on the surface in this picture, right? Well, okay, how would I do it? So let's say I want to draw this curve. Let's say I want to draw the curve, 2, 4. So that's one of the things that we were talking about before. Okay? So how would I draw 2, 4 in this world? Well, it's a little bit annoying, right? Because here, what is 2? 2 is this kind of black region here. 4 is this sort of black region here somehow, right? So if I want to draw a curve from 2 to 4, I have to sort of find something that maybe starts here and then ends there somewhere. Okay? That's perfectly okay. We could talk about that. But it's a little funny to anchor these curves. It's not obvious where to put it. Okay, I could put it anywhere along here. There's a more natural thing that you can do. There's something more natural in this picture, which is also here. When I talked about the sort of curve 2, 4, these black dots are somehow telling me that 2 and 4 don't belong to the surface. But to denote what I mean by 2, 4, let me draw instead something which is the same curve, but I just tilt it slightly, the whole picture, let's say clockwise. Okay, so I'm going to draw it from a little bit to the right of 2 to a little bit to the right of 4 instead. Okay? Now it's obvious that I can go forwards and backwards between these two pictures because we're talking about orientable surfaces. It's obvious here for this case, but also for any surface. What it means by rotating to the right is well defined because there's a well-defined notion of orientation on the surface. to surface aficionados, these, I don't remember what they're called, but these things are maybe called, I call them chords, and these things are called, well, to surface aficionados, we'll call them laminations, and we call them just curves. Because this is a chord, this is a curve. All right? And so the curve is easier to draw in this picture. The curve 2, 4, well, it just starts up here somewhere. A little bit to the right of 2, so it starts in 2, and then it meanders around, and it exits at 4. Right? All right? So every variable, remember, this is so much of this entire story of positive geometries and amplitudes are about thinking about kinematic space. The big surprise is you think hard about kinematic space, and kinematic space has way more structure than you would have naively thought. So in Carolina's story, the kinematic space is just the xij's. What could be exciting about xij's? There's just a bunch of points on a grid. But you draw the points on a grid, and then all of a sudden, oh geez, they're repeated twice. So I have to find a chunk of the grid in which they all occur once and only once. And oh geez, that brings to life these funny triangles. And then the whole story starts developing from there. Okay? So we're doing the same thing now, except we're really starting from scratch. We're just taking, this is our picture. We know that kinematics are associated with these chords. We're defining our surface by drawing one of these pictures, and I just want to learn how would I draw 2, 4. The way I would draw 2, 4 is in this slightly more natural way by going slightly to the right of 2, taking that road, going out, and moving slightly to the right of 4. Okay, so is that clear? Every xij, which is a kinematic variable, every xij is naturally associated with some chord ij, which is further, more naturally associated with the curve ij. Okay, its cousin curve ij. Okay? Okay. Now something very interesting happens. So, I hope it's clear we haven't done anything yet, right? We're just drawing a picture, and now we know how to describe every variable, right? Every variable is some curve in this surface. Okay? So for example, even the ones in the triangulation, 1, 3 is not just that segment. 1, 3 would look like this curve. Okay? Every single variable is some curve on the surface. The kinematics are associated with curves on surfaces. Okay? Okay, and now remember we saw in the previous in our discussion from the first hour, kind of 2 magical things happen. One, the first one was that starting from the association, etc., we got this fan, which was cones. The cones correspond to diagrams, and they tiled the entire space. Okay. So that was already one remarkable thing. And the second one was that we could somehow efficiently generate those cones from these polynomials and the tropicalization, right? Those were the 2 ideas. I'm now, in the time I have, I'll be able to explain or at least show you the first magical thing, and then tomorrow we'll pick up and talk about the second one, okay? But the first magical thing is that we're going to see where cones come from. They're going to cover the entire space, okay? And we're going to do that without, by just listing all of these curves. Right? So we're now going to talk about how would you present a curve. Okay? So let's say you're blind. You couldn't see the picture, and you just wanted to tell someone what all the curves were. Okay? All right. Well, what we're going to do, and it's the only reasonable thing to do, is we're going to give the Google Navigate instructions for how you would drive along the road corresponding to this curve. Okay? So you want to say, I want to follow, 2, 4. Again, I'm living in this universe, okay? But let me draw this picture slightly bigger and less messy. Okay? And this is my world. This is also my map, and if I want to take this road 2, 4, then, well, I could label all these roads. I mean, I could label this road. This is road A, B, C, D, E, F, G. Okay? Let me slightly more reasonably label the roads in this case just by, you will forgive me if I label this road 1, 2. I think it's clear what I mean by that, right? It's bounded by 1 and 2. 2 and 3, 3 and 4, 4 and 5, 5 and 1, 1 and 3, 1 and 4. This is not always possible, but in this very simple example, we might as well label the roads like that. You can also label them A, B, C, D, E, F, G. That's fine, okay? And now, what is that road? I just have to do what Google Navigate would tell me to do. So,
Sorry, what do you mean by this is not always possible? Like,
I mean, it's not always possible to uniquely label a road by the things that touch it. Sometimes, I mean, in very complicated surfaces, this is not always possible, but it's not necessary. This is just in this example for convenience.
But probably like non-planar things.
Yes, that's right.
Okay.
Yes, exactly. Yes, in the planar cases, it's always possible. Yes, that's right. So, for example, here I start on the road 2, 3, and Google Navigate says, make a left turn onto the road 1, 3. Okay, so all you're going to do is give instructions. All you can do, by the way, there's one caveat on these roads that I draw. All you can do is travel along a road till you get to the next intersection, and then you can turn left or right at that intersection. And that's it. You can't double back. You can't go halfway down the road and decide, oh, I changed my mind. I don't want to go down this road. That's the only thing you're not allowed to do. Otherwise, you just proceed until you hit the intersection and you go left or right. So it says I start on the road 2, 3. I make a left turn on the road 1, 3. And then I make a right turn on the road 1, 4. And then make a left turn onto the road 4, 5. Okay? So this is what you could call the word for the curve 2, 4. Okay? Every curve has a word, right? Which is just the Google Navigate instructions. So let's do another one. Let's do one of these simple ones, like what's this curve? That corresponds to 1, 3. This would be we start at 1, 2. I make a right turn on the road 1, 3, and then make a left turn onto the onto the road 3, 4. This would be the word for 1, 3. Okay? So every curve has a word. All right. Now, there's a very obvious and natural way to keep track of all of these words. You can make associated with any one of these curves and these words what you can call the geometric vector of the curve. So I'm going to call that for a curve C. For a curve C, I'm going to define the geometric vector. You can call it geom of C. And this lives in a space whose dimensionality is equal to the total number of roads in the picture. Okay? So in this case, it would be a 7-dimensional vector, because I have 7 roads. I erased the picture, sorry. Draw this for the umpteenth time. Okay? There's 7 roads in this picture, 1, 2, 3, 4, 5, and the 2 internal ones, 7 roads. So this would be a 7-dimensional vector. And what is this 7-dimensional vector? In this example, it would be labeled by 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, and the internal ones 1, 3, and 1, 4. And just the entry is just the number of times the curve visits that road. That's it. Okay, so in this case, it would be a 1, 1, 0 vector. Okay? So for example, the geometric vector for the curve 2, 4, the geometric vector for this curve 2, 4 has a 1 in entries 2, 3, 1, 3, 1, 4, and 4, 5, and 0 everywhere else. Okay? So the geom of the curve 2, 4 would be, just as I said, 1, 1, 1, and 0 everywhere else. Okay? So this 7 vector. Okay? I hope you agree, so far so boring. Nothing interesting is happening yet. Okay? I have my surface that I've defined by the parent fact graph. I draw all the curves. Each one has a geometric vector. I have a big stack of geometric vectors. Okay? In this problem, how many geometric vectors do I have? I have 10 geometric vectors. Let's look at, because I also have geometric vectors for these boundary curves. Let's say I take this curve 1, 2. This is just one of the boundary curves of the problem. It has a geometric vector, right? This guy is the geom vector for this sort of boundary curve 1, 2 would just be 1, 1, 0, 0, 0 for everyone else. Okay? Okay, so both the 5 internal curves and the 5 external boundary curves each have geometric vectors that are 7-dimensional. Okay? So far, there's nothing good about these curves, good or bad about these vectors. They're just about the positive vectors and the positive orthants because they all have plus signs, right? Okay? Now comes the cool thing. This is the sort of surface avatar of going on shell. Okay? Because there is, after all, a distinction between the boundary curves and the internal ones. We don't associate variables with the boundary curves, right? They're on shell. We only care about the variables for the internal curves. Okay? So what is a natural way in this picture of ignoring the boundary curves? How would you go about ignoring the boundary curves? The most natural way to do it is to just project through them. Okay? So in other words, you have all these geometric vectors, they're sticking out in various directions, but you don't really care about the curve 1, 2. So I'm just going to look at the whole picture in the direction of the curve 1, 2. So 1, 2 is gone. I've projected through 1, 2, and I've gone down to a 1 lower dimensional space. Okay? And I'm going to do that with all of the boundary curves. I'm just going to get rid of all of the boundary curves. Okay? Just by projecting through them. When I do that, I'm going to go from a 7-dimensional space to a 5-dimensional space, right? Now the space is more natural. The dimensionality is just the number of internal propagators. Okay, I'm just projecting through 5 vectors. And okay, I'm going to be now all of the boundary vectors are mapped to the origin, of course, because I've projected through them. That's the whole point of mapping them all to the origin. And I'm left with the 5 remaining ones in a 2-dimensional space. Okay?
Sorry, but there are like 2 internal propagators.
There's
right?
2 internal propagators. That's why the space is 2-dimensional. There's 2 internal propagators. Space is 2-dimensional. I still have 5 curves though that are not boundary curves. I have the internal curves that are left. So I'm going to have 5 2-dimensional vectors. I started with 10 7-dimensional vectors. 5 of them were boundaries. 5 of them were internal. I project through the boundary guys. Notice projecting through the boundary guys is not the same as just truncating the top 5 components, right? Because the boundary vectors are interesting vectors in this geometric space. I project through them, okay? I project through them, but I end up with a 2-dimensional space, okay? All right, now that's just a linear algebra exercise. It's trivial to do the linear algebra exercise. I'll leave it for you as an exercise to do it well right now, by doing it in this super direct, dumb way. But I'll write down what it looks like when you do it. So you're left with a 2-dimensional vector space. And so, I can choose any basis I like for the 2-dimensional vector space. Of course, it's natural to choose the basis. It's natural to choose the basis to be the one that you get by projecting 1, 3 and 1, 4. 1, 3 and 1, 4 were defining in the triangulation, so they're clearly somehow special. So let me just tell you what happens after you project through the boundaries. After you project through the boundaries, you get a 2-dimensional picture. So I'm going to choose as a basis, this is what 1, 3 turns into. Just a basis of 1, 3 and 1, 4. And guess what, of course? 2, 4 is that vector. 2, 5 is that vector. And 3, 5 is that vector. Okay? Exactly the picture that we had before. Except I didn't do anything. I didn't start with ABHY, isosahedron, blah, blah, all of Carolina's talk. Forget about it, right? We're just defining the surface, recording all the curves, and then this one interesting operation of projecting through the boundaries to be the kind of analog of forgetting about them. We don't care about them. We project through the boundaries, and then instead of having the stack of vectors all with positive coordinates, in the positive orthant, after I project, I get this picture. And miraculously, amazingly, I get something that tiles the entire space, and the cones are Feynman diagrams. The cones are triangulations of the surface, which are Feynman diagrams. Okay? I find this absolutely remarkable, right? Because this, in a very concrete sense, is like all the pictures of all the space-time processes just come out. Just come out with no thought. Okay? They just come out from this automatic operation. Now, I'm going to tell you the rule for reading off these, this picture without this work. And you'll also see from the nature of the rule what the proof is, that it corresponds to the process that I was telling you about. In order to do this, let me go back to the picture. And let's look at some of our words again. Except I'm going to denote the words slightly differently. Actually, here we are. Okay. So let's say I have this word. I'm going to draw it. Instead of writing LR, I'm going to make a little mountainscape out of it. Whenever there's an L, I'm going to draw something going up. Whenever there's an R, I'm going to draw something going down. Okay. So from here instead, I would write this as 2, 3, up to 1, 3, down to 1, 4. Up to 4, 5. Okay? Now, what instead would the word for like this boundary curve? Let's do this boundary curve. Let's say we do this one, 5, 1, right? What does this look like? It looks like 1, 2, right onto 1, 3, right onto 1, 4, right onto 1, 5. They all go right, or they all go left. Okay? They went backwards, that all go left. So for example, yeah, so that one would look like 1, 5, up onto 1, 4, up onto 1, 3, up onto 1, 2. This is what a boundary curve looks like. It's all up or all down. But these guys, internal curves have interesting ups and downs in them. Okay? And so this should make it obvious what the formula is for the vector associated with these curves after projection. The vector associated with these curves after projection are called g-vectors. Not geometric vectors, but g-vectors. Okay? And the g-vector for a curve C can be read off in a very simple way from its word. Okay? So the g-vector, not the geometry vector, but the g-vector for the curve C is simply equal to the sum over all the valleys minus the sum over all peaks of the word. Okay. What I mean by this is that you imagine associating a basis element with each one of the internal words. Okay. So I'll just call that, I could call it E13 and E14, although I'll sometimes just call it 1, 3 and 1, 4. But then what is the g vector associated with this word? The 1, 4 is a valley, so it's positive E14. The 1, 3 is a peak, so it's minus E13. So the g vector for 2, 4 would be E14 minus E13. And indeed, if you look at the picture, that's what we got for 2, 4, right? Plus E14 minus E13. Okay? So you can easily see why this peak minus valley formula must be correct, because this is just a linear map on the original vectors. And this linear map has a job to do. It has to send to 0 everything which is all upward going. So that's why it cares about peaks and valleys. Okay? You have to have a peak or valley in order to get something non-zero. And a moment slot shows this is essentially the unique linear map that has a property that it sends all the upward or downward going things to 0 and preserves the rest of them in some way. All right? So let's now pause. Yes?
So, but this is now the g vector that comes from the cluster algebra stuff?
In this case, this is a g vector that comes from the cluster algebra. As I said a few times, for general surfaces, the cluster algebra is not quite the right thing. Okay, and so that's why I keep insisting on this difference. Also because it ruined a year and a half of my life, sort of thinking that the cluster algebra was the right thing. So it was not the right thing, and so I still have a lot of energy about it. But yes, here in these examples. It's the same as the g vectors you'd associate with the cluster algebra. All right. So we have 5 minutes left. So let me just sum up. Okay. So what you can do, and I invite you to try this in the just in the next example, for a 6-point disk or a 6-particle tree amplitude. Draw your favorite fact graph for it. You know, our favorite fact graph for many purposes has been this one that Carolina was talking about, where you just add more and more things to it. Okay, so you could draw something like that, Or, at 6 points, you could draw something like this Mercedes-Benz type picture. Okay? So draw any of these pictures you like. Any one of these things gives you an equally good triangulation of the surface, equally good Parrot-Fact graph. Okay? And then just write, in this case, there's 9 internal curves. So draw 9 curves, make 9 words, make 9 sets of peaks and valleys, 9 sets of g-vectors. Plot them, just in mathematical, or by hand. Plot them, and see to your wonder that they form cones. And each cone corresponds to a particular way that these 3 curves can come together and give you a triangulation of the surface, right? You didn't ask for it. It's just plonking down the names of the curves, drawing the projections, and it just automatically divides the space up into these cones, right? Now, the proof of this statement is relatively easy. It has to do with the fact that if you take a random geometric vector, so we can step back. I gave you a definition of the geometric vector. But you can step back and say, if I hand you a random vector, how do you know it's a geom vector for something? Okay? Can you check whether some vector, all positive integer entries, how can I check if it's a geometric vector of something? And in fact, there's a set of inequalities that there's a sort of cone, what you call the geometric vector cone, that specifies all possible consistent geometric vectors, okay, given a surface. Very simple picture. I'll say it in the language of triangulations. Maybe I'll just draw it here. So let's say you draw any set of, either a single curve on the surface, or indeed any collection of, and here's the important word, non-intersecting curves on a surface. One, maybe the surface is very complicated, the curve comes around, circles in lots of ways, or I draw 10 curves on top of each other that are non-intersecting, okay? But the sort of key thing is that you're drawing a bunch of non-intersecting curves. Then what can these curves look like in any triangle in the triangulation? Okay, so here's some triangle in the triangulation. This giant collection of curves, what can it look like inside this triangle? It has to look like this, right? There can't be anything that crosses through this triangle, otherwise there'd be crossing, okay? So if this is the edge A, an edge B, an edge C in the triangulation, and so if the geometric vector, if the component is some integer A, some integer B, and some integer C, then in order for this to be compatible with this picture, if there's X things going through here, Y things going through here, and Z things going through here, then we have to have that X is equal to A plus B. The other way. A is equal to X plus Z. B is equal to X plus Y. And C is equal to X plus Z, which we can invert to solve for X is equal to A plus B minus C over 2, and so on. Okay. Did I do that right? No. Let's see. X should be. Did I do this right? Sorry. C is Z plus Y. Sorry about that. Okay. So now this is correct, right? So A plus B minus C is 2x. So X is A plus B minus C over 2, and so on. Okay. So that means that these numbers A, B, and C have to satisfy that A plus B minus C over 2 is greater than or equal to 0 integer. Okay? So that's how you can check. If someone hands you a random geometric vector, you have to just check the stack of inequalities, right? So they hand you the triangulation, so you know what all the ABCs are for all the triangles. You just have to check the stack of inequalities, and that will tell you if it's a legal geometric vector. Okay? And now there's a cool point, which is obvious when you think about it, but one of those things you have to just think about it a little bit. I don't know. I can give a formal proof, but the formal proof is harder than just thinking about it, which is the following. So first of all, given any picture like this, you can also decide whether this corresponds to a single curve or multiple curves. Okay, and on top of each other, and basically there's essentially an algorithm. Like pick a strand here and just follow it. See where it goes, right? If it goes and you sort of exit the surface in one place or another, then take it out. If there's anything left, it's not a single component curve, right? There are other curves around, right? So you can decide whether you have a single component curve or not. And the final comment then is that given any legal geometric vector is uniquely represented as a positive integer sum of single component geometric vectors. Okay? That's a sort of key point, is that you can uniquely say, given any legal geometric vector, which set of curves have been put on top of each other in a non-intersecting way to preserve it. Once you know that fact, it's really a few line argument to say that after you project to get down to the G vectors, that you get that there are the cones, that A, if you make a cone out of single component curves that don't cross each other, then such cones cannot intersect. Okay, so that's a very, very simple consequence of this fact. So that tells you that the cones that correspond to triangulations do not overlap each other. And B, you can see that they cover the entire space. And there's a very simple argument that the linear span of all these cones must cover the entire space, because we get the positive orthant for free out of the parent underlying curves, right, that go into the triangulation. But there's also a set of curves that are the negative orthant. And who are they? Remember, right at the beginning of this story, we made a choice of whether we're going to rotate the curves to the right or to the left to define them. I just chose to rotate them clockwise. Well, if you rotate all the curves counterclockwise, you get another set of curves on the surface, and their G vectors are precisely the negative of the ones where you do it the other way. Okay? So there's in fact two sets of, there's a positive orthant and kind of a negative orthant. So together, that guarantees the entire space is covered. Okay? So these two arguments together tells you that, that the entire space is tiled by cones that correspond to triangulations and that cover the entire space. Okay? So in the end, it's a very simple argument. But it's still quite remarkable again that this is an algorithm that you can quickly put on a computer, generate these G vectors. There's a bunch of cones, and so I've made all the diagrams, all the triangulations have sort of come out for free from this extremely simple point of view. Okay, so what we'll pick up on tomorrow is the more interesting, maybe much more interesting aspect of this story. That is, as we emphasized already, but I'll just say it again before we go. It's one thing to know that all the diagrams come to life just by recording all the curves and projecting down to G vector space. But it's still not useful for computing an amplitude if what you have to do is in every cone go and compute something for the cone and add them all up. Then we're just doing finding diagrams all over again. The more interesting second fact is that we can, this whole fan, sometimes called the G vector fan, or we call it the Feynman fan. Okay, this fan is the result of the common refinement of a bunch of simple tropical functions, or that there's a bunch of polynomials that are associated with these pictures, and most fundamentally, there are U variables associated with all these pictures. Okay? And the magic is going to be that we're going to find a way to solve the U equations. Okay, we're going to present the solution to the U equations. I'm going to tell you how to give a formula for every U, right? Now, you might think these U equations look very global. I mean, that's the whole point. They're somehow telling you how curves interact with all other curves, right? So this curve, what are the other curves it intersects? The U equations feel very, very global. The amazing thing is that there's going to be a totally local formula for the U's. In other words, if you give me a curve and the word for the curve, from the word for the curve, there's going to be a simple computation that gives you the U variable associated with that curve without looking at any of the other curves. You don't even think about the other curves. Someone just hands you the word for a curve, and we're going to give a very simple formula that's associated with a nice combinatorial counting problem associated with that word, whose solution is going to be the U variables. Okay? So that's the somehow magic of this story, that while we can prove it and understand it in various ways, I still feel is not completely understood. This local, global fact that the U variables can be computed entirely locally from the knowledge of the word specifying a curve, and yet they know to do this thing to solve the U equations and keep all of the, and control the combinatorics of how all of these curves come together. But once we get those U variables, we'll see the polynomials that go along with those U variables. The U variables will be associated with certain polynomials. These polynomials are called F polynomials that are associated with the curves. And they give you the stringy integral in both the forms, in the integral u to the x form, as well as the form where you just write down powers of y and polynomials to the minus c. Okay, so those are the two forms, and they tropicalize to give you the global Schwinger parametric form for the amplitude. So that's the first part of what we'll talk about tomorrow, is where these u variables come from. All right, thanks a lot.